to still do the admit. Right, people are coming in. Cool. And I think we are live. Hello, everyone. Welcome and thank you very much for joining. We are waiting a few minutes more before starting, just so everybody can have the time to come in, and we will start the live session very soon. More people are coming in the lobby. Let's wait a few more minutes. We will start probably around 3:03. Okay. And let's admit. For the ones who just joined, we're waiting a few minutes more just to make sure everybody has the time to attend and follow our live webinar from the very beginning. Still people are queuing. We are admitting them all. This is nice. Okay, a few seconds more and we start, I would say. Let's just make sure everybody can follow from the beginning. This very exciting webinar. Because today we are introducing to you something we're quite excited about. Okay, a few more seconds. And I would say maybe we can start. Okay, Paul, can you hear me? Just to double check everything is
yes,
okay.
Yes, loud and clear. Can you also hear me?
Perfectly.
Okay.
Okay, then I would say let's start. First of all, thanks everyone for joining. My name is Marco Mattia Cristofori. I'm product marketing manager here at BSF Forward AM. A few things before we deep dive into the webinar. Your microphone and cameras are turned off by default, so don't worry about that. We will do that also to ensure that Paul has his peace of mind during the presentation. Generally speaking, we really value your active participation to the webinar. So you can see on the top, you should have a Q&A button. So during the presentation, you can already start writing your questions and leave them there. We have a little moderation, but generally we will accept all the questions, obviously. And at the end of the presentation of Paul, we will try to answer all of them. If the time ends and we didn't answer all the questions, fear not. We will make sure you get an email with the answer as soon as possible. Another thing to keep in mind: this webinar will be recorded. So by participating, you're consenting us to be recording. The recording will be shared with you after webinar, in addition to the slides, but also other additional materials. Generally speaking, if you need more information, we are always available, so you can reach out to us whenever you want. Let's dive into the actual webinar. First of all, for the one who are not familiar with us, we are BSF Forward AM, and we offer the world's largest selection of 3D printing materials and service solutions. We are basically spread all around the world, so you can find us easily. Today we talk about one specific material in our portfolio. We're talking about filament, and we're talking about one of our latest release. We call it PLA Tough. We like to positioning as the ultimate functional PLA. If you are in the industry, you might have realized that the market now is filled with high-speed filament, but we realize that speed alone solves only so part of the equation, and that's why we developed this material, which is a material that is not only compatible with high speed, but has a lot of superpowers in addition to it. Who's going to introduce you to this material? One of our amazing product manager. Today with us, our speaker is Paul Shepard, and my pronunciation in Dutch is not that good, so most probably the surname is not well pronounced. Sorry, Paul. Paul has been working with us since 2021, and he has a background in mechanical and biomedical engineer. He is currently responsible for the entire life cycle of our extrusion material portfolio. including several of our Ultrafuse filaments. At this point, I leave the stage to you, Paul, and I want to remind you guys, or the ones that just joined, there is a Q&A session, so feel free to drop your questions during the presentation. Paul, again, stage is yours, and see you later.
Okay, thank you, Marco, for the introduction. So welcome all to this beautiful presentation. We're going to talk about the ultimate functional PLA, Ultrafuse PLA Tough. So what's on the agenda for today? So first of all, we are going to do a deep dive in the full, true high-speed solution that we offer at S4AM. Then, why did we develop an Ultrafuse PLA Tough product? We will go into each of the superpowers of this product. Then we will showcase some use cases of this specific product. And then let's say we have a small teaser, and that is that we are going to demonstrate the toughness of this product by bouncing a ball. So does it bounce or does it break? And then we have, let's say, the Q&A session at the end of the presentation. So at 4AM, we are striving to give a true full high-speed solution. So what does that mean? So for us, that means that we have, let's say that we have three main pillars to achieve this high-speed solution. That means you have a high-speed material, you need a high-speed design, and a high-speed process. So if we dive into the high-speed materials on the top of this triangle, then you see that we have Ultrafuse high-speed filaments. And you can recognize our products by the clock icon. So this little icon. And these are mostly model materials, but that's, let's say, not enough, because if you are working in FDM, you also want to make complex parts. And therefore, you sometimes need support materials. So we did a partnership with Xioneer that develops support materials. And together, those combinations, so Xioneer support materials with our modeling materials, can give you a true high-speed solution, because both materials can be printed in high speed. So besides this, we have a high-speed design. So as you probably are aware, you need to design for additive manufacturing, but you also need to design for high speed. And within 4AM, we have an application technology center. We call this ATC, and a solution department. So if you want to have a design and you want to validate this for high speed, we are here to help you and assist you to make the design for this particular application in high speed. And then we have the last step of a triangle, that is the high speed process. So if you have a high speed material and you have a high speed design, you also need equipment that is able to process the materials and the design in high speed. So for example, you need high speed printers like a Bamboo Lab that's quite known at the moment, or other printers. So not that long ago, you were able, let's say the standard in 3D printing was printing at 40 millimeters per second. Nowadays it goes up to 300 millimeters per second with a raise, or even 500 with a Bamboo Lab, or even higher. And when you print it, you also need to post-process those products. For example, if you use Xioneer support material and you want to remove it quickly, Xioneer's, let's say, support you with equipment that also allows you to remove the support material in a quick manner. So those three steps are all needed to have a full, true, high-speed solution. And also to relieve you, we develop customized print profiles and also customized high-speed print profiles. They're more or less the recipe for your printer to high-speed print the material. And that is what we think is a full high-speed solution, because we think that speed alone only solves parts of the equation. So you need all the three pillars. So as already mentioned, today we are going to talk about the ultimate functional PLA, Ultrafuse PLA Tough. And the two main UVPs of this product are toughness and high speed. And I want to, let's say, introduce you to those two properties. What is it? How do we evaluate it? And how could it be utilized by you, the customer? So first of all, the toughness. So toughness is actually the resistance to fracture. So toughness reflects how well a material resists cracking or fracturing. And let's say if you look in the material properties, it could be described by two basic properties. That is strength and ductility. Strength, this refers to how much force a material can withstand before it breaks. And ductility is the material ability to bend and deform without snapping. So how do we measure it? So you see the icon, so the hammer, that is showing impact. And this is actually also how we are more or less measuring it. So we use ISO standard, like a Sharpie or an ISO test in, let's say, conditioned environments. And then we, let's say, move this hammer and smash it into a sample of printed material. And then we record actually the measurement. And this gives us the amount of energy that is absorbed by the material before it breaks at the notch, for example, a notch material or an unnotched material. And this is a measure how we measure the impact toughness. So, and this is something that is quite important for materials that might experience certain impacts during use. So how is this utilized, this particular property? So toughness is crucial for many applications. For instance, for those who drive a car, you have car bumpers. And if you, let's say, drive to something into a wall, for example, I don't hope that it will overcome you. But in general, the car bumper doesn't scatter in multiple pieces. It dents. And this is something that is related to the toughness of the material. Or for example, if you look from the other side, I think most of you have seen in their lifetime a glass that dropped on the floor and it's scattered in multiple pieces, in multiple fractions. So this is a material that is not tough, it's brittle. So actually, this is the toughness. And teaser alert, in the end of this presentation, we will demonstrate the impact resistance of a ball. I think you know this ball. This is the famous airless ball that everybody is talking about. So I hope you can make it till the end of the presentation because it's a nice demonstration to see. So then we go into the high speed portion. So what is it? So I think in the previous slide I already introduced how we as 4AM are providing a true high speed solution. But I will go a little bit more in depth to understand how we evaluate high speed printing. So as already mentioned, not that long ago, the standard was printing at 40 millimeters per second. So that translates roughly to a volumetric flow rate of 3.2 cubic millimeters per second. And let's say nowadays, we need to define a new standard. And those products, so our Ultrafuse products with this clock symbol, we have, let's say, given a strict requirement of, let's say, at least 8 cubic millimeters per second. That translates to an 0.2 nozzle with a nozzle of an 0.2 layer height with a nozzle of 0.4 and printing at 100 millimeters per second. So our PLA Tough, how fast can that print? 300 millimeters per second. And a volumetric throughput of 24 millimeters per second. So how can you benefit from this property? So I think most of us do agree that we want to print more and weight less because that allows all kinds of benefit, like a higher throughput, but means that new business cases can be established as within this high-speed solution. So I think we all agree on that this high speed in combination with a material property like toughness could bring us all benefits. So just to record it once again, this icon, when you see it in our Ultrafuse products, it is able to print at least a throughput of 8 millimeters cube per second. But if technology evolves, maybe the printing speeds can even become higher because it's also related on the equipment that is utilized during the print. And we are also looking, of course, on the surface quality and the mechanical performance of this material when printed on high speed. So Ultrafuse PLA Tough. So why did we develop it? So if you have, let's say, PLA and an ABS material, both have, let's say, a unique set of properties. PLA is an easy to print material. And ABS, let's say, has quite some toughness, but they also have some weaknesses. So PLA in general tends to be brittle. So that means it snaps and fractures quite easily. ABS is very tough. However, it could warp or delaminate. And it also is, let's say, it's fossil based. And with a PLA, it's a bio based. So, and we like to close those two gaps of those particular products with the Ultrafuse PLA Tough, because PLA and ABS together, they are the major market in FDM. So what are the superpowers? So Ultrafuse PLA Tough is a highly versatile, biocompatible and bio-based material. So it's easy to print with this material. It's a sustainable and cost and time saving production, especially for large but also fine detailed prints. So it's actually quite suitable for functional applications for beginners, but also for seasoned 3D printer experts. So what are the 8 superpowers? So as already mentioned, it's tough. It's really tough. So with the impact resistance of 34 kilojoule per square meter. And we can also even enhance those superpowers by annealing it. And how does it relate to a standard PLA? So it's 720% more tough than a standard PLA. I already talked about high speed. So this material can print at this moment with current equipment up to 300 millimeters per second. And maybe with newer technologies, it can go even faster. But it is also biocompatible. That means that it is safe to use on the skin. And we have done all kinds of tests to evaluate if there are no allergic reactions. And we also have a statement about this. Besides this, it's also crucial that the part looks good. So it's aesthetic and visual appealing even when printed on higher speeds. Then the heat resistance. So standard, the PLA Tough is not that heat resistant, but as already mentioned, we can enhance superpowers. And that is also something that we can do with annealing the part. We can increase the heat resistance up to 157 degrees Celsius. So therefore you can also use this PLA Tough material in high temperature applications. Then it's post-processable. For example, CNC milling, it's easy to sand, but you can also coat or paint it. It is a bio-based material because I think most of you know that a PLA, polylactic acid, is derived from corn. And its use, it can be used for large scale to fine detail prints. So these are the 8 superpowers, and those add value to you. Just to summarize it, so it's 720% tougher than standard PLA. So the PLA Tough, as already mentioned multiple times, is able to print at higher speeds with a volumetric flow rate up to 24 cubic millimeters per second, suitable for skin contact, and has a high success rate to print with complex geometries and large-scale prints and fine details. And it's also compatible with a water-soluble support Ultrafuse BVOH. It's stronger than the ABS, 130% stronger, and it's bio-based. And we can anneal it to enhance its superpowers. Let's look a little bit closer how this annealing process looks like. So when you're printing a part, you print actually one material next to another layer on top and top and top of each other. And what actually happens during this printing is that you get, let's say, internal stresses of this design in the design. So what happens when you heat it? So actually you can anneal the polymer material by a heat treatment that involves subjecting a polymer to a controlled heating and cooling cycle. During this, let's say, cooling and heating cycle, the polymer chains, let's say these internal stresses can be relaxated because the crystals and the polymer chains can actually position themselves in a more favorable state. And because they are in a more favorable state, the properties also enhances. So like mechanical properties are enhanced, the wear and the thermal properties of this specific material. So how does a heat cycle, let's say this annealing setup look like? So we have 3 steps. First, you need to have, let's say, an oven or a furnace that can heat up to 120 degrees Celsius. You need to ensure that you fixate your part in a sufficient way, and then you go into the heating phase. So you heat it from room temperature up to 120 degrees Celsius for about 50 minutes. Then you stay at this particular temperature for about 30 minutes at 120 degrees Celsius before you go enter the cooling cycle. And the cooling cycle actually drops the temperature from 120 degrees Celsius back to room temperature. So this entire process takes about 1 hour. And we have evaluated this on a particular specimen, and you can actually look in the technical data sheet for more details about the annealing procedure. So let's look on how these properties are enhanced by annealing it. So on the left, you see how we enhance the thermal properties of the specific product. So in the light blue, you see, let's say, unannealed PLA Tough, and in the darker blue, you see annealed PLA Tough. So what you see is that the at this, for example, in a load of 10 newtons, so normally it has a heat resistance for about 60 degrees Celsius, and for a load up to 10 newtons, it can resist 157 degrees Celsius. That is almost 260% more. So that's a huge increasement in a, let's say, in a thermal property. But also the toughness can be increased. So for example, if you look at the notched and the unnotched materials, for a notched version, it's about 230% more. So that's a significant increase. Of course, is it only the superpowers that we can enhance? No, that's not all. There's also a small, let's say, setback, but a setback that you can control. So what happens during the annealing, that in the different orientations, you have, let's say, a shrinkage or an increase in dimensions. So the shrinkage in the XY orientations, it's, let's say, -1%, and in the Z orientation is 2%. And in the design of your model, you can already think about this particular shrinkage rate and compensate for it, so that the final dimensions of your part are reached after the annealing set. So how to choose the right type of material? So probably for those who are aware of a portfolio, you have seen that we offer multiple PLA products and also an ABS. And I want to give you a, let's say, a rule of thumb, how to select the right material for your application. So if you want to use a standard PLA, we offer PLA for an affordable, easy, and colorful 3D prints with no warping, ideal for basic projects and beginners. If you are considering high speed and an excellent, perfect surface quality, then we advise Pro 1. It's for the top tier 3 printers that demand the best aesthetics. It's slightly tougher than PLA, but the fastest to print with no warping issues, so ideally for premium projects. Further, it's also biocompatible and it's for the professional users. Then we have ABS. It is as tough as our PLA Tough. However, if you want to be let's say, think about the environment, a PLA is a bio-based product and ABS isn't. Furthermore, ABS emits styrene emissions during printing, while PLA Tough doesn't. So it's the more sustainable option. So in general, you could position the PLA Tough between the Ultrafuse PLA and the Pro 1. It's a more affordable option that gives you all of the benefits of an ABS. So what do we offer? We offer technical data sheets and safety data sheets and quite a large range of languages. We provide you with a biocompatible statement, and we have all kinds of reads and substances of very high concerns documentation available and other safety aspects. Furthermore, we also provide you with sustainability information for the products that are produced within Europe. And yes, this product is produced within Europe. Furthermore, it's BPA and BSA free. And all documentations are available. So Ultrafuse PLA Tough as an alternative for ABS and standard PLA. So let's have a deep dive in the material properties. So what you see here is a spider graph of a lot of properties. In general, how this works is the larger the surface area of particular properties, the better it is for certain applications. Although it's also depending, of course, on the final application field. But in general, the larger the area, the better it's performing. And in blue, we have PLA Tough. So we know that PLA and ABS have both, let's say, limitation. PLA is quite brittle, and ABS, let's say, isn't the most suitable material if you think about the environment or if you want to print without styrene emissions. But it also shows, for example, one of the most crucial factors in FDM printing is that you, if you want to have very strong parts, you don't want to have delamination, and delamination occurs quite often in the Z orientation. What you see on the top is that for both a PLA, so in the green, and in the black, an ABS, or PLA Tough is outperforming it. So, and that's quite unique because that is in general the most weakest link of your print. And if you, for example, look on the impact tests, you see that it is outperforming also on ABS. Sometimes it's quite close. But if you need, let's say in general, heat resistance, then always go for an ABS material. However, you can compensate by annealing it. So the PLA Tough, if you anneal it, you enhance the superpowers. And that is reflected in this area. So normally in blue, you see, let's say, the heat resistance of the material over here. And we can enhance these properties by annealing it. And then you see that it increases the thermal resistance. So it comes quite close to an ABS material. And of course, it's stronger than an ABS, as already mentioned before. So now we come to the topic that we are going to present some use cases. Although we have many use cases for the PLA Tough, unfortunately, due to non-disclosure agreements, we are not able to showcase them all. But we can, of course, show something. But before we start, I want to share how you as a user can already feel the toughness of this product. And that's actually when you have, let's say, the filament in your hands, you can already, let's say, see it and feel it. So this is a colleague who's demonstrating, let's say, to break the filament. And I think for those people who are used to working with PLA, they know how easy it is to break. And yeah, I speed it up 5 times and you see it's not that easy, but also you can think about it in a different way. So in the past slide, you have seen, let's say, the spool sizes from 750 grams up to 8 kilograms. And those big spools are also quite heavy. And where do you use this very large reels? General for very big, large scale prints. And if you need to, let's say, pull the filament from this heavy spool, you don't want to have it, let's say, that the filament snaps. And especially for a print that takes maybe several days to print. If it snaps during the print, maybe you need to print it again. And with the PLA Tough, it gives an extra piece of reliability that it will not snap during this higher, let's say, consuming materials in this big and large scale prints. So the impact resistance. So this is a problem within the company that the material solves. It is a functional fixture. This is an internal use cases where hundreds of parts are CNC milled out of PLA Tough for, let's say, in this case, to evaluate the material properties. And to really clamp the parts into the fixture, you see that my colleague is actually hammering some wedges into this white PLA Tough substrate to ensure that the part will not move during the milling operation. So both the fixture as the wedges are fully operational to us today, even after hundreds of, let's say, clamping the part inside the fixture and hammering the wedges inside the white part. And they are going to exist for a long time to serve us for a longer period. Oh, and did I mention that the PLA Tough is very easy to post-process? like for example, CNC milling? It is. So this is a beautiful application from the Victoria Hand Project. That's a Canadian charity that uses 3D printing to create affordable prosthetic arms for people in need worldwide. So Victoria Hands focus on reaching those areas where traditional prosthetics care is limited due to high cost or lack of resources. So their 3D printing prosthetic hands are designed to be functional and accessible to who otherwise wouldn't have this option. For example, wars in Ukraine has left many grapplings with devastating injuries, and they are actually supporting the material, the trainings, and the printers to those locations so that they can print this kind of prosthetics on demand in this particular zones. So actually, Victoria Hands supports hands, helping recipes regain independence, hope, and opportunities to live a happier and more fulfilling life. So this is just an example how a prosthetic is used. So you can imagine yourself that Victoria Hand has, let's say, two main challenges. Because they print it on demand locally, they need to have an easy to print material. So PLA Tough is suitable for this specific area. But on the other hand, it also needs to be durable and strengthy because it needs to withstand the daily load cases of everyday wear and tear. This can involve anything from your daily household routines like cooking, cleaning, or grasping an item. In this case, the person is trying to pick up the scissors from the table. But it could also be during playing sports, like the prosthetics should withstand those loads when bumping into somebody. So therefore, it's crucial that the material needs to be durable enough to handle those activities without breaking or wearing down too quickly. And maybe you already recognize that a lot of things are going on in this particular design. So let's have a closer look on those functional applications, because it is the ultimate functional PLA. So on the top, you see actually a functional design of a rotatable thumb. This rotation is used to achieve different positions, allowing to grasp, let's say, different objects from a table. Then there is this backlock mechanism that lets the user actually lock the hand to close something. So you see, when you, let's say, tick into this backlock mechanism, the hand actually could hold an item. And there's also a composition of multiple materials. So you see some screws that are inserted into the PLA Tough, and you see some chains that actually is combined with some metal parts. Then we have, let's say, an adjustable or rotatable wrist that actually locks the hand into different positions. So that it's easier to pick up other parts from a table, for example. So, and lastly, we have an adaptive grasp control. So if the shape is a little bit different, you see that not all fingers move at the same, let's say, distance, but they adjust according to the object. So this is another use case that shows a pneumatic regulator mounting. So this was used in a continuous manufacturing setting, and actually a unique challenge arises. They need to install a pneumatic regulator on new machines within one production shift of 8 hours. So that's quite a tight schedule. And normally, let's say you could order maybe such a jacket, but if you are such a fixture, but within 8 hours, I doubt that you actually can have, let's say, the order already available at your doorstep. So actually traditional methods proved to be insufficient. So actually they changed to 3D printing and to our PLA Tough because they were aware of this durability and of course the design freedom of additive manufacturing. So what did they do? So they were aware that the PLA Tough is, let's say, is high-speed compatible. And what they did is they designed the part from scratch to actually have those unique, what is it? So these are locations specifically designed for, let's say, the cavities are designed to mount it directly on the machine, and they have a unique location. So they are designed for this. The second step is they need to print it. And with the PLA Tough, they are able to print it, let's say, in a quite a reduced amount of time because of the high-speed profiles that we have created for them. So normally, you would able to print those with about 13 hours to print. And now with the high-speed printing profiles, you're able to reduce the printing time to 3 hours. So that's a 250% reduction in time. And then the last step is, of course, the assembly on the machine. So all of those steps are done within one working day. And that is something that you can combine with a high-speed material and, of course, additive manufacturing. So this is another use case from actually a colleague of mine. So it's high-speed printing in combination with the tooling for a mountain bike. And yes, this tooling went up to the Atlas Mountains. So my colleague actually came to the rescue. So the neighbor of my colleague, he booked a trip to the Atlas Mountains for a biking trip, a mountain biking trip, and he wants to change his gears, let's say to have a more comfortable ride. And he already ordered some tools, but when he tried to actually replace the direct mount chain rings, he actually ran into a problem. The tool that he had ordered didn't fit. So he asked my colleague, like, hey, can you please help me? I'm going to the Atlas Mountains. I need an adapter. And he didn't have, so my colleague didn't have an adapter. So what he did, actually, he downloaded this design that you see here, specifically for let's say the gears that are needed. And within 1 hour, they had a text message. He printed it. And in 1 hour, he also had, let's say, the new gears installed on his bike for him to have a more pleasant ride. So this use case shows actually the potential of additive manufacturing in combination with high-speed printing. So it's more or less on demand within the same hour, I would say, creating a more comfortable ride. So this is the last use case we are going to present. This is, let's say, as already mentioned, the PLA Tough is a biocompatible product. That means that it's suitable for skin contact. But it also shows, in this case, the fine, intricate curves and fine details and sharp overhangs. So those complex geometries can be printed by using our Ultrafuse BVO8 support materials, and it just shows that you can use PLA Tough for orthotics that need a more rigid material. So we're coming to, let's say, the ending of the presentation. And as already promised, I would show you a real-life example of how PLA Tough is comparing to a PLA with an impact test. And we printed this airless ball multiple times to show you the following. So what you see is that there is this translucent or transparent 2-meter high tube. And on the bottom, you see a concrete tile. And what I will do for you is I will, let's say, bounce this ball multiple times on this concrete plate, and we will look how the materials behave with respect to each other. So we are now at 2 versus 2. And yes, I will go and speed up the video. You don't need to wait forever. Actually, I was expecting during this test that the PLA Tough would fail a little bit earlier, but to my expectation, let's say it went on quite a long period of time. So at 8 times, the standard PLA fails, and the Ultrafuse PLA Tough is still going strong. So almost up to 20 times of dropping the ball. And I think it's now time to increase the speed even more. And you could even see this as an exercise. So at that moment in time, it was time, let's say, to cool off a little bit. So 52 times. 52 times until failure. And we repeated this experiment 3 times. And on average, let's say this PLA Tough is 611% higher before it fails. So failure means that the ball is not bouncing back because it's fractured on the shell. So what are the conditions? The ball is about 140 grams plus or minus 2 grams. So for those who are into physics, you can do some calculations to determine the loads on the ball. The height of the tube is 2 meters high, and we repeated the test 3 times. And on average, let's say the PLA Tough failed after 26 times of dropping the ball from a 2-meter height, and the standard PLA only 4 times. And this shows actually how this material could behave in a real life environment. And this is of course quite extreme, to drop a ball on a concrete plate from 2 meters high. So all you need to know for Ultrafuse PLA Tough. So it's one of our engineering filaments for those who need a pro material. We offer this particular product from 750 grams up to 8 kilogram in a diameter of 1.75 and 2.85. And at this moment, it's available in black and a natural color. And it's available within Europe. But if you are in another region like Americas or Asia, please reach out to your account manager and we are happy to assist you to get this material in your region as well. Furthermore, we have, let's say, the print profiles available for many different brands and slicers. So for all of our material print profiles, also for, let's say, other products in PLA Tough, we have those print profiles available at our material landing pages on our website. That means that all the time and effort that went into creating those profiles is available at your fingertips. And if you would like to read more information about our use cases, please scan the QR code and you see more use cases and more details about the use cases. So I give back the ball to Marco, and he will ask you some questions before we go into the Q&A session.
First of all, Paul, thank you very much. It was a great presentation. I love the video, the comparison. Those are always the best way to understand, what you mean when you go into technical details. So it works very well. Unfortunately, we got some messages during the live. The Q&A, it's not working, even though we tested it a gazillion times. If anyone wants to anyway ask a question right now, you could try to raise your hand. There is a button to raise your hand, and then we unmute you so you can ask your question live with your microphone. This could be an option. Option B, keep your questions, and as soon as we reach out to you via email, you can always ask us the questions back. We will give you our contact soon anyway. So up to you. In case you feel like asking a question with your microphone, I think you have a raise your hand button on the top, so we could unmute you. I know not everybody is comfortable with that, so completely understand if you want to keep your questions for the email. In the meantime, if nobody raised their hand, Paul, we have one. Okay, let's give it a try. We have two. Okay, let's give it a try. I think I can allow the mic. I hope I can. Let me try.
Yes, can you hear me?
Yes.
Yes, perfect. Loud and clear.
Okay, nice.
Yeah.
Hi. Okay, thank you. Hi, thank you guys for the presentation. I just wanted to know if you have performed some electrical characterization on your material, like for example, current tracking index, CTI test, or dielectric rigidity. Can we find this kind of information on the technical datasheet?
So an HCT test, is that correct?
CTI, current tracking index.
So at this moment, we have not performed those tests, and they are not available in the technical data sheet. But you can reach out and request those tests, and maybe we can perform them for you for a specific application.
Okay, thank you. For information, I am in a railway industry, and we are particularly interested by material able to withstand very high voltage for electrical insulation applications.
That is good to know. So we have actually some dedicated materials in our portfolio that are validated for various railway tests and applications. So I think I'm confident that we can find a solution for this. Thank you for your question.
Thank you again for the presentation.
Yeah. Thank you for your question.
Thank you very much. We have another one. Bal M, I think you're already unmuted.
Yeah. Hi.
Hi.
Thank you for the presentation. Very interesting. So my question is, assuming the price between the tough and the regular PLA is not an issue, is there any other reason for choosing regular PLA versus the tough one? I mean, can I replace the regular PLA by the tough one in any circumstance? Isn't there any shortcoming? I don't know.
So actually, that was one of my follow-up questions for you as the audience. So at the moment, if you want to use our Ultrafuse PLA, we offer this in a very, let's say, colorful portfolio. So if you are into colorful prints, I would recommend at this moment in time to switch to standard PLA. And my follow-up question to you, let's say to all the folks that are joining the meeting, what is the colors that you want to have next? So at the moment, I feel that you can actually switch from PLA to a PLA Tough if you need more, let's say, toughness or high-speed applications. To my knowledge, there are no limitations. The only drawback is the variety of colors that you have available, that we have available at this moment in time. So you can see all the colors that we have available in PLA, and we don't have this at this moment available for PLA Tough.
Yeah, thank you for the answer. I'm targeting like functional prototypes, so the colors are not important. But sometimes, if any order for a colored product will arrive, I'd rather go for the tough just in case versus the regular one.
That is very good to hear.
Yeah, I'm mostly printing consumer products, and
consumer products.
Yeah, the brittle nature of the regular PLA is a big issue for.
Yeah, that's something we also found. So, what kind of things are you printing, for example? Could you give an application?
It's just prototypes for consumer products. I can send you some models, but yeah, I don't have anyone around me.
Okay. Thank you for asking this question.
We will anyway follow up with email, so then you guys can also go deeper in the conversation. Okay, I'm glad this raise your hand works. I like it even more than the Q&A that written.
Yes.
It's nice to hear other voices. Anyone else has questions? This is your time to ask to Paul. It's very hard to catch Paul. He's always very, very busy. So this is your chance to actually get his full attention for your question. Otherwise, we go back to the last slides and we can close it up. Anyway, I see that the time is anyway running. Cool.
So shall I go back to the last slides?
Let's do that. So we will ask you this question then via email, probably, if you guys want to help us to figure out what's the next color for our PLA Tough, right?
Indeed, yeah. So we are looking into making also colors available for PLA Tough, and we would like to know your opinion for colors. So please let us know. We will ask you the questions by our follow-up emails, and you can reply on this. And we also have a second question. I already asked one of you. So what kind of applications are you using at the moment PLA, and what kind of application are you considering Ultrafuse PLA Tough? We would like to learn from you to actually, if you develop a new generation products, we also know what you are, what the current, let's say, weaknesses of our portfolio are, and how we can strengthen the new developments, material developments.
Okay, we can follow up with these questions via email. The Q&A, this is what it is. If you guys want, it's the last seconds, otherwise we can close up. You find our contacts here. If you scan the QR code, I believe it goes to our LinkedIn page, so you can also reach out there. Otherwise, these are the emails for more technical content related. Paul, if you're interested in anything that goes also beyond filament, as mentioned before, we offer any kind of additive manufacturing material, but also services and solutions, so powder, resins. We help with design for additive manufacturing, simulation, LCA, etc. In those cases, you can also reach out to me, and I will then make sure that you get in contact with the with the person you need to talk with. From our side, that's it. A last slide, because we mentioned some references during the webinar, and it's important to highlight those. So here is more what have you have seen in the amazing slides of Paul's. Again, as mentioned, you will get the recording of the webinar in case you have colleagues that couldn't attend, so they can watch it later. As well, you will have the presentation and additional information as well. Do not hesitate to reach out to us. We're always here and happy to help you. And that's it. So thank you very much for attending, and I wish you a great rest of the day or evening or morning, depending where you're located.
Thank you very much.
Bye, everyone.
And keep printing. Bye.
Keep printing. Oh, I see it was a question. Well, I guess we will reach out later.